This is Cisco Training 6. This is Daryl. Today we're going to talk about RIP version 1. This is the format of a RIP version 1 packet. We have 8 bits for the command, although really there's only 2 different commands that are used. One, which is request, where you're requesting routing information, and 2, which is reply, which is where you're giving out routing information. Ironically, routers reply more often than they request, meaning that routers just spontaneously give out information and actually rarely request information with RIP. We have the version number. Today we're talking about RIP version 1. We got 8 bits here, so we're talking about version 1. These 16 bits must be 0. The address family identifier is here. This is IP version 4 that RIP version 1 works with. And I think that's encoded as a 4 in here, but I'm not really sure. This section here must be 0, another 16 bits. Then we have our IP address of the route advertisement, and then we have 32 bits of zeros, and then we have the metric. Even though the metric is 32 bits here, the metric in RIP is a hop count metric. How many router hops is it to that destination? And so it'll start at 1 and then hop count 2 and then hop count 3 and so on. 16 is considered infinite. So the maximum number of hops that you can have is 15. It's either 14 or 15. We'll see. So stepping back a little bit, RIP is a dynamic routing protocol. In the last session we configured static routing. In order to set up our 3 routers, we had to set up 9 static routes in order for routing to work properly. And then if we renumbered any of our interfaces, we'd have to change static routes on all of our routers. That's a real pain in the neck. It's very error prone. A dynamic routing protocol is designed to automatically update your route table. So that way it's more accurate because the computer is doing it for you. Why would you want to do it when the computer can do it for you? So that's the good news with dynamic routing protocols. The bad news is they're more complex, but that's what network engineers do. Network engineers, we exist to route traffic to the destination, and the routing protocols are our friend. RIP is Routing Information Protocol. It is a very primitive routing protocol. RIP version 1 is an old version of it, which is called classful, meaning that it just uses the network subnetting of the classful network boundary. Meaning, if you're in a class A, RIP assumes that it's a /8. If you're in a class B, it assumes that you're in a /16. If you're in a class C, it assumes that you're in a /24. Note in the packet format here, we have the IP address of the route advertisement. So if we're advertising a route like 17 if we're advertising a route like 10.12.0.0/16, well then we'd have 10.12.0.0 here in the IP address. But where do we put the /16? We put the metric down here, but there's no place to put the /16. So what's funny is when router A is talking to router B, router A advertises the route, but it only advertises the route portion. It doesn't advertise the subnetting because RIP version 1 can't handle subnetting. It's just not designed to handle it. And we'll see how that impacts us. Okay, so this is the packet format. This is payload in a UDP packet. UDP is User Datagram Protocol. We haven't talked about TCP/IP theory yet, but it's a connectionless protocol. It goes out on UDP port 520 is set aside for RIP. Let's look at our network for today. Here's the network we're going to build today. It's a triangle very similar to what we built yesterday. One difference is we've changed our IP addressing, but the other difference is we have made everything a /24. And that's because RIP version 1 can't handle variable subnetting. For more efficiency, we'd make our loopback /32s our point-to-point link /30s. RIP version 1 just can't handle that. So RIP version 1 can handle a subnet mask that's different, like a /30 or a /24, but you have to pick one in your whole network. And we'll see some examples of that when we get to our debugs. Okay, so let's start configuring our routers. So we'll start at the top. We're going to start out configuring our IP addressing for everything, and then we're going to go back and configure our routing. Host name top, int loopback 0, IP address 772.16.1.1. This is a /24, so it's 255, 255, 255.0. No shut, int serial 0, IP address 172.16.2.1, 255 to 255, 255.0. No shut. This is DTE, so I don't need the clock rate. Int serial 1, IP address 172.17.2.1, 255.255.255.0. No shut. Clock rate 64,000 because this is DCE. And that is it for this router. Let's go to the next router. This is the middle router. What I did is, before the session, I did a write erase, and then I did a reload. And so that way our routers are in fresh host name middle, int loopback 0, IP address 172.16.3.1, 255.255.255.0, int serial 1, IP address 172.16.2.2, 255.255.255.0. No shut. This is DCE. Clock rate 64,000. Int serial 0. IP address 172.17.1.1, 255.255.255.0. No shut. This is DTE, so no clock rate. And we should be able to ping 172.16.2.1, and we should not, which is the serial 0 interface in the top router. We should not be able to ping 172.16.1.1, which is the loopback interface in the top router, because we have not configured any routing protocol. And that's working as expected. Let's go to the bottom router. Host name bottom, int loopback 0, IP address 172.17.3.1, 255.255.255.0, no shut, int serial 0, IP address 172.17.2.2, 255.255.255.0, no shut, int serial 1, IP address 172.17.1.2, 255.255.255.0. Clock rate 64,000, no shut. Now we should be able to ping. Show IP int brief. Up on everything. Ping 172.17.2.1. That's across our serial 0 interface to the top router. Ping 172.17.1.1. That's across our serial 1 interface to the middle router. So we've now tested all of our links. They're all working. Now let's configure our routing protocol. Conf t router rip. This puts us, so just like when we do interface serial 0, it puts us into an interface configuration mode. When we type in router rip, it puts us into a routing protocol, a routing protocol configuration mode. So we're studying RIP version 1. So I type in version 1 just to keep us on version 1. Then what I need to do is I need to turn on routing on our interfaces. Now RIP is classful. So what you do is you use a command called network 172.17.0.0. This will turn on This will turn on RIP on all interfaces which are in 172.17.0.0. Looking back at our map, 172.17, all three of our interfaces on this router are in that network. Just for kicks, let's type a couple other network statements. 10.17.0.0 and network 192.168.17.0. Now let's do a show run pipe begin router RIP. We'll see if that. Okay, our router doesn't like the pipe begin command because we're running an old version. Let me see what version we're running. Yep, we're running 11.3 on this, 11.3 on this router. So I'll just do a show run. More modern versions of iOS let you start. So here's the router RIP, version 1, but notice this isn't what we typed in. We typed in 172.17.0.0. 172 is a class B because the first bit is 1 and the second bit is 0. So the natural net mask is a /16. So when we typed in the network statement, it kept the first 16 bits, which we typed in, and made the rest zeros. Well, we typed in 172.17.0.0, so that didn't do anything. On the other one, on the 10 net, we typed in 10.17.0.0. But 10 net is a class A because the first bit is 1. And so what it did is it kept the bits of the network for the class A, which are the first 8 bits, and it changed the rest to 0. So even though we typed in 10.17.0.0, it interpreted as 10.0.0.0. This will turn on RIP for any IP address where the first octet is 10. Whereas in this one, in this network statement, it will only turn on RIP on all interfaces in where the first 2 octets are 172.17. And here we have class C address space, 192, where the first bit is 1, the second bit is 1, the third bit is 0. In this case, the natural net mask of a class C is a /24. So it keeps the first 24 bits, changes the rest to 0. So it will only turn on routing for IP address on RIP routing on interfaces which start with 192.168.17. So what happens sometimes is people type in 10.0.0.0 and that turns it on for the whole 10 net. Then they type in 172.0.0.0 like this. Conf T router RIP network 172.0.0.0.0. They think that that will turn. They think that this command will turn on routing on all interfaces which start with 172, but they're wrong. This is a class B. It will turn on routing for all this line will turn on routing for all interfaces which start with 172.0, which means that our IP addresses with 172.7 which start with 172.17 are not turned on by this. The routing protocol is not turned on by this network command. We're still okay. All interfaces on this router start with 172.17, so our routing protocol configuration is done. Let's look at another new command, show IP proto. This shows all routing protocols that are enabled on this router. Routing protocol RIP. RIP sends updates every 30 seconds. The next is due in 23 seconds. So 23 seconds from we executed this command, we will send an update. A route that we receive, if we will receive that route about every 30 seconds from our neighbors. If we do not stop receiving the route, we will still consider it valid for 180 seconds or 3 minutes. So every half minute, we're expecting the route advertisement, but if we don't receive it for a whole 3 minutes, a whole 6 cycles, then we consider that route invalid. And then what we do is, for another 3 minutes, because the route just went invalid, we basically don't believe updates for that route for a few minutes, because the network is converging. And to help it converge, we don't want to listen to any correct information. So after we declare a route invalid, for 3 minutes we won't believe any advertisements for that route. And then flushed after 240 just means 4 minutes after we hold it down, we'll just drop all references that we ever received the route from our routing table. Outgoing update filter list. We can filter our outbound updates if we want with an access list. We don't have a filter list right now because I didn't configure it. Incoming update filter list. Again, we don't have any updates. We don't have any inbound filters. So there's nothing there. It says redistributing RIP. All that means is we receive routes via RIP and we send them on via RIP. That's default. In fact, I don't know any way to turn that off. The only question is whether we would be redistributing any other protocols like static routes. Default version control. Since I typed in version 1, we are sending version 1 and receiving version 1. That's the default on all of our interfaces, sending version 1, receive version 1. And on each interface it tells you I'm sending version 1, I'm receiving version 1. It tells you what networks we're routing for, basically what interfaces we have RIP turned on. And routing information sources. These are other routers that we see that are sending us RIP advertisements, but we don't see any RIP advertisements. Then we have something called distance. The default distance is 120. This is called administrative distance. This is how believable the routing protocol is. The problem is there are multiple routing protocols. There's RIP, there's EIGRP, there's OSPF, there's BGP. If you receive the same route via 2 separate routing protocols, which one are you going to believe? So the way Cisco lets you do the comparison is it assigns each routing protocol an administrative distance. The lower the administrative distance, the more believable that routing protocol is. The lowest administrative distance you can have is 0 for a connected route. So you will believe a connected route over any routing protocol. A static route has an administrative distance of 1. So a static route that you configure manually on the router is more believable than anything except a connected route. EIGRP is 90. OSPF I think is 110. RIP is a very primitive routing protocol, so it has an administrative distance of 120. So it is not particularly believable. If you receive a route via OSPF and via RIP, you're going to prefer the OSPF route. Let's do a show IP route. We can see our connected routes here. Our 3 subnets that are directly connected out. Interface serial 1, loopback 0, and serial 0. We don't have any RIP routes left yet. Why don't we have any RIP routes? Because we haven't configured RIP on any other routers. RIP is used to communicate routes between routers. So far we've just configured RIP on the bottom router. Let's go ahead and go to another router and configure RIP. Okay, I'm on the top router now. The top router has IP addresses in the 172.16 range and the 172.17 range. Let's make a mistake. conft router RIP version 1 network 172.0.0.0. If I was typing in network for the 10 net, it would be network 10.0.0.0 because 10net's a /8. But this is a class B because 10net's a class A. 172net is a class B. I'll type in 172.0.0.0. Show IP proto. you can see I'm routing for networks 172.0.0.0. But you know, back up here where we had the version control, send version 1, receive version 1, there's no interfaces listed here. That's because there are no IP addresses where the first 16 bits are 172.0. Okay, so let's fix it. T, router RIP, network 172.16.0.0, network 172.17.0.0. I need to configure them both because this router has IP addresses in the 172.16 range and the 172.17 range. Okay, let's, okay, so we got our routing protocol configured. Let's do a show IP proto. And what's changed? Well, we now have our default version control is still send version 1, receive version 1, but we have 3 interfaces where we're sending version 1 and receiving version 1. And this is interesting. It says automatic network summarization is in effect. What that means is, well, we'll see what it means with some debugs. Basically, we have this, whenever we have some of our interfaces in the 172.16.0.0 class B, and some of our interface, and one interface in the 172.17.0.0 class B. So when we're advertising this class B out an interface inside this class B, then in effect we have to automatically summarize it. Let's go ahead and, and here's a routing information source, 172.17.2.2. This is our bottom router out our serial 1 interface. And so you can see it, we received an update just recently. Let me do it again. Our last update was 18 seconds ago, which means we'd expect a new one in 12 seconds because RIP sends updates every 30 seconds. Let's do debug IP RIP and see what there is to see. Again, this is less dangerous than the debug IP packet, but it is still dangerous, particularly in a large network, because RIP advertises every route advertisement every 30 seconds. No debug all. Okay, so let's go ahead and look what happened. RIP sending version 1 update to 255.255.255.255. So we are broadcasting this update out the loopback interface. And our source interface is 172.16.1.1. What are we sending? We send 2 route advertisements, 172.16.2.0 and 172.17.0.0. This is interesting. Looking back at our network, 172, this is our loopback interface, we're sending it out. First of all, we're not sending out 172.16.1.0. We are sending out 172.16.2.0. And we're not sending out 172.17.2.0. We're sending out 172.17.0.0. Okay, so the first thing, why are we not sending out 172.16.1.0 out the loopback interface? Well, that's something called split horizon. You don't send out route advertisements on the interface you receive them on, and in this case, it's a special case, you don't advertise a subnet out that subnet's interface because any other router that's attached to that subnet knows that it's attached to that subnet. So why would we tell them to send the traffic to us? They're already directly connected to it. Okay, we do send out 172.16.2.0, that slash 24, but You notice this update, it doesn't say it's a /24. How does this router know it's a /24? The answer is it doesn't. In the RIP version 1 format, nowhere in there is the subnet. It's just not in the protocol. The only reason any router that would happen to be out this interface would know that this advertisement is a /24 is because this subnet that it is directly attached to is a /24. And the subnet that it's directly attached to is in the same classful subnet. In RIP version 1, they assume that any particular classful subnet is always subnetted at exactly the same number of bits. So a router that happened to be up here would know that this 172.16.2.0 advertisement is a /24 because that router is connected to this subnet, which is also in the same class B and is a /24. That brings us to the reason for this 172.17.0.0 advertisement. We should have advertised 172.17.2.0 /24. But this is in a different class B. So there's no way for a router up here to know what the subnetting is for this class B. So instead, this router sent out what's called an automatic network summarization. It sent out a just 172.17.0.0. It advertised the whole /16. That's a little bit risky. The good news is we're advertising that subnet, which means that we're advertising the whole address block, which means that a router out this way will be able to know that, hey, the 172.17 net is that way. But we can only deliver to a few /24s inside the 172.17 range. If there happens to be another 172.17 in some other location, then we might actually draw the traffic away from it. So one of the things with RIP version 1 is it assumes that any particular classful net has all of the subnets physically attached to each other. In a later session, we'll see what happens when you split them up. So that's this routing advertisement. We have 3 subnets attached to this router, but we only sent out 2 updates. One of them was 172.16.2.0. One of them was 172.17.0.0. That's the routing advertisement out the loopback. Now here's a routing advertisement broadcast out the serial interface. This is serial 0. It sends out the 172.16.1.0, which is the loopback's address block, and then it also sends out the automatic network summary for the 172.17.0.0, the whole /16 class B. And then out serial 1, we only send out one route advertisement. This is the automatic network summary for 172.16.0.0, the whole /16. So out this interface, which is in the 172.17 net, we should be advertising this subnet, and we should be advertising this subnet. But since they're in a different classful subnet, we just summarize them and advertise the whole 172.16.0.0 /16. Because if we sent out something like 172.16.1.0, there's no way for the bottom router to know what the net mask is. All the bottom router knows is, because the net mask is not part of the RIP version 1 protocol. There's no place to put the net mask in there. So the only information that the bottom router has to guess the subnet is the subnet that we got it on, but that doesn't work for in this case because it's a different classful block, or the fact that it is a classful block, so you use the sort of the native net masking, native subnetting of the classful block. Okay, so that's automatic network summarization. let's go ahead and do a debug IP, do another debug IP rip. Let's see if we can catch a incoming network update. And we might have to wait up to 30 seconds to see it. So we'll just hang out. And there's an update. No debug all. Okay, so on our serial 1 interface from the bottom router at 172.17.2.2, we received a RIP version 1 update. The update had 2 route advertisements, 172.17.1.0 in one hop and 172.17.3.0 in one hop. What's the subnet associated with that? Well, we don't know the subnet from the RIP packet that we receive because RIP version 1 doesn't have a subnet in it. So since those advertisements are for 172. For address blocks inside, they're for 172.17.1.0 and 172.17.3.0, we have an interface attached to the 172.17 net, which is a /24. Therefore, we assume that what we received is a /24. So let's look at what we installed in our route table. Actually, let's show IP RIP database. So RIP is a routing protocol. It maintains its own database of what it's received. And so it knows that, like, here's a directly connected /24, another directly connected /24. Here is a /24 that we received from this router. We received it 2 seconds ago we received it on our serial 1 interface. We received it from this router, so this router will be our next hop. This is the RIP database. This is not a routing table. We do not forward packets based on the RIP database. RIP is a routing protocol. It updates the RIP database. The entries in the RIP database are candidates for our routing table. We may or may not put these entries in our routing table, depending on whether we believe them or not. In this case, RIP and connected routes are our only routing database entries, so to speak. So we will install these RIP routes in our routing table. But if we were running OSPF, then we would have to choose whether to believe the OSPF database or the RIP database. And that's when it gets us back to administrative distance. The administrative distance of RIP is 120. The RIP, the EIGRP is another routing protocol. EIGRP is an administrative distance of 90. Lower is better. So if we have the same route in our EIGRP database and our RIP database, we will believe EIGRP. So let's look at our route table. Show IP route. So here's 172.17.1.0. It was learned via RIP. It's a /24 because here this whole class B, 172.17.0.0, we've decided it's all subnetted in a /24. So this RIP entry is 172.17.1.0/24. Its administrative distance is 120 because that's the default administrative distance of RIP, and we didn't change it using the distance command. It is 1 hop away. RIP talks in turn. RIP's metrics is hop counts. It doesn't care whether your router, your interface that you're receiving it on is a frame relay link or whether it's a 10 gigabit Ethernet link. A router hop is a router hop, and 16 router hops is infinite. This is our next hop, 172.17.2.2, out serial 1. We received it 22 seconds ago. So this is our RIP. This is our route table. Let's do a show IP Ceph. Ceph is not running. Conf T. I'm going to enable IP Ceph. That will increase our routing performance by a factor of 10, but there is a cost involved. The cost is the extra memory necessary to run, to have a optimized version of our routing table, which is easier for the router to forward. So show IP route, now show IP Ceph. The Ceph table is very similar to the route table. It has for each subnet where to send it. So like for this subnet, we send it, for this subnet 172.17.1.0/24, we send it to 172.17.2.2 out serial 1. Okay, so let's go back. Was there anything else to look at in that RIP advertisement we received? I don't think so. So let's move on. Show or debug IP RIP. Let's look for an example of another example of split horizon. So we might have to wait up to 30 seconds again here. We could play the Jeopardy theme. Dun, 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 dun. Oh, there we are. No debug all. So we received on serial 1 this route advertisement for 172.17.1.0. As a result, this route entry is in our RIP database. It is in our route table. It is in our Ceph table now that we've enabled Ceph. Now here is our serial 1 interface. We sent an update, but you know, we didn't send, even though this entry is in our RIP database, we didn't send it out. Why not? The reason is because this is an advertisement going out the serial 1 interface, and we received this entry on our serial 1 interface. This is another example of split horizon. Why advertise a route out an interface? Why advertise a route advertisement out an interface that you received it? If there were any other routers on that subnet, they would have already received it from whoever sent it to us. If we sent out the route advertisement, which basically when you send a route advertisement, you're saying, hey, send packets to me, I can reach this subnet. Well, why would we send it out this way? There's another router out there that's one hop closer, and it's already advertising for that subnet. That is split horizon. Now let's deal with a triggered update. So debug IP RIP conft int lo0 shutdown. No debug all. Okay, so what happened? We shut down our loopback interface. Our loopback interface has the 172.16.1.0/24 subnet. So it went down, and so then RIP sending version 1 flash update to the broadcast address via serial 0. And so then we send this flash update. It says that 170.16.1.0 is now metric 16, which is infinite. So here's what we did here. We sent a triggered update. Since an interface went down to make the network converge faster, and by converge that means propagate correct routing information, we sent an update immediately which said that this subnet is unreachable, because an infinite metric means unreachable. We also wanted to send a flash update out serial 1. But out the serial 1 interface, we were sending the 172.16.0.0 automatic summary. And it is still appropriate for us to send that because we still have a 172.16.0.0. We still have a subnet inside 172.16.0.0. So as a result, we don't have any update to send out serial 1. So that's what the suppressing null update means. We considered sending a flash update out the interface, but When we actually did the calculations and figured out what to send, we didn't have anything to send, so we didn't send it. Now conf t, actually and debug IP rip conf t int lo0 no shut. No debug all. Okay, so we just brought up a interface, the loopback0 interface. So what did we do? One of the things we did is we sent a RIP request out loopback0, basically saying, hey, are there any routers out there? If there are, please send me your routing information. There are no routers out there because it's the loopback interface, but that's sort of interesting. That's the first time we've seen a request. Until now, it's always been an update. Again, in the routing protocol, the RIP protocol, the first 8 bits are the command. 1 is a request, 2 is an update. Almost everything we've seen so far has been an update. Hey, here's some routing information. This is the first time we've seen a request, which is, hey, I just came up. Tell me what your routing information is quickly. Okay, so we sent our request. Then the other thing is we were going to send a flash update out the loopback interface, but we ended up not sending it. I'm not sure why. Let's move on. We did send a flash update out the serial0 interface with the loopback interface on it. So basically since a new interface, since a new subnet just came up, we decided to propagate that information immediately as opposed to waiting for the next 30-second regular scheduled update. So that's called a triggered update. And then we considered sending a flash update out our serial1 interface, but we're already sending out the summary for the whole 172.16, so there was nothing to send. So there I do know why we suppressed the null update. Okay. That is it for RIP version 1.